then for this, because you guys have the math down well, is some of the language and some of the like actual showiness that you need in order to like answer the question fully. Okay, so you guys are doing the right process. It looks really, really good. I want to expand upon that and put some verbiage to that, just to make it a little bit logically more sound, if that makes sense. So let's take a look at A here. So we are trying, given the function f of x is equal to this piecewise function of x squared plus 5x plus 6 over x plus 1, if x is less than or equal to negative 5 over 3, and it's equal to x plus 1 if x is greater than negative 5 over 3. And we are trying to show that it is continuous everywhere, which is a fairly high burden of proof, actually. And it is a fairly high burden of proof that we cannot approach directly using our limit definition over and over and over and over again. If I'm trying to show that this is continuous everywhere, then I'm going to run out of time within my lifespan trying to show that it's continuous everywhere between 0 and 1, let alone that it is continuous for every single number, right? There are an infinite number of numbers for which I need to demonstrate that this is true. We could not do so by just like checking every single point individually. We simply would not be able to. So instead of doing that, we need to make a very broad statement about most of the values for this function, and then maybe demonstrate continuity for one that is potentially problematic. So looking at this particular function, given the kind of piecewise nature of this function, what is the value of x where I should be worried about whether or not it's going to be continuous there? Okay, two answers that I really, really like. So I heard -1 and I heard negative 5 over 3. The answer I was looking for was negative 5 over 3, just because that's the one that's represented here. But I don't want to, I actually really like this answer. Harrison, why did you say -1? Okay, so we have the potential to be dividing by 0 if our top equation is ever, if x is ever equal to -1 while we're using our top equation, right? So there are actually a couple of problematic values, potentially problematic values anyway. We have one, which is the piecewise nature. We have one that is potentially dividing by 0. So if I want to kind of hone in on that -5 over 3, then we're going to kind of make two general statements here. We're going to talk about what is going on if our value of x is less than -5 over 3 and why we might be continuous there. And we're going to make a very similar statement for what is going on if x is greater than -5 over 3, and then we'll do like a separate thing for like that point itself, which is what most people that I saw did. Okay, so Harrison has brought up an excellent point, which is that we should be very worried about continuity for our top function because we have the possibility to divide by 0. But I still would like to claim that we have continuity for every single value of x. Why do we actually not really need to worry about dividing by 0 for our top function? -5/3 is our kind of cutoff. It's the largest possible value that we could use for the top equation. And so we never reach -1, right? We don't use this definition for our function when x is equal to -1. And so we might make a statement along the lines of f of x is continuous for all values of x, assuming x is greater than, assuming x is less than -5/3, because we can use direct substitution with our x squared plus 5x plus 6 over x plus 1 for all of our x's that are less than negative 5/3. Right? Negative 1 is really the only one we could not do direct substitution for, but negative 1 is not less than negative 5/3, so we don't really need to worry about it. Okay, so we're good if we're to the left of negative 5/3. If I'm to the right of negative 5/3, which function am I going to be using? Bottom function. And is there a point that is to the right of negative 5/3 where I wouldn't be able to do direct substitution with the bottom function? No, we're going to be totally good. And so we can make another statement that is like f of x is continuous for all x because exact same thing we can use direct substitution with x plus 1 for all x greater than negative 5/3. Also for all x, but since we only really care about the ones that are greater than negative 5/3, we can go ahead and add that condition there. Okay, so we have continuity if we are to the left of negative 5/3. We have continuity if we are to the right of negative 5/3. It's kind of trivial continuity. We're saying it's kind of continuous because it's continuous, but it's fine. What then is really the only value that we need to actually demonstrate for our continuity? The negative 5/3 itself is the only one that we actually care about. All right. But I will say, if I asked you this on, say, I don't know, like a quiz we had tomorrow, and you didn't include some kind of statement like this, like, oh, I can use direct substitution for all of these values, I can use direct substitution for all of these values, therefore we're good and continuous for all of these values, then you would not be demonstrating that this is true for all values of x. So it's really, really, really important. This is not just me in my kind of classic self being overly verbose. This is what you would need. You would need to say something along these lines to get full credit for this kind of question. Okay, so now let's do our continuity check at negative 5/3. So continuity requires 3 different things in order to demonstrate that we are continuous. The first and third are going to come very naturally. The second one is really the hard one. And the second one is the one that I saw most people doing very, very well. But we do want to make sure that we are going through our full list. What is the very first thing that we need to demonstrate to claim that our function is a continuous function at negative 5/3? Yeah, we have to first say that f of negative 5/3 exists. Okay, so for f of negative 5/3, which function am I going to use for this? We'll use the top one, that's the or equal to. So plugging that in, I get that this is negative 2/3. Does negative 2/3 exist? Yes, therefore, first check is good. Our function is defined at that point. Which like 99.99999% of the time it will be, but it is important to check. It's like just a quick little check, just make sure. Okay, what is the second thing that we need to demonstrate? Yeah, we have to demonstrate that the left-hand limit and the right-hand limit agree. So we are looking at the limit as x approaches negative 5/3 from the left. And we are looking at the limit as x approaches negative 5/3 from the right. Okay, for this piecewise function, if I'm looking to the left of negative 5/3, which equation will I use? Top equation. This is the limit as x approaches negative 5/3 from the left of x squared plus 5x plus 6 over x plus 1. Do I have any domain issues here that would prevent me from doing direct substitution? No. And in fact, direct substitution giving me the exact same thing that I saw from example 1, that this is negative 2/3. Okay. What about our right-hand limit? Which function will we use if we are to the right of negative 5/3? We'll use the bottom one here. So this is the limit as x approaches negative 5/3 to the right of x plus 1, which is also equal to negative 2/3. Do these agree? Yes, they do. And so our overall limit as x approaches negative 5/3 of f of x is negative 2/3. And stating what it is also good enough to say that, oh, hey, by the way, it also exists. Right. That is certainly a demonstration that it exists. Okay. That's the, like, you'll notice that that's like the mathy bit. But again, it's important that we're doing all the steps here. What's the final step? Again, basically something that we've already demonstrated, but it's just kind of putting the puzzle pieces next to each other to make it super, super obvious. Yeah, so now we're saying that, okay, our f of negative 5/3 we found was equal to negative 2/3, which is the same as the limit as x approaches negative 5/3 of f of x. Therefore, f of x is continuous. You could say everywhere here, like you could literally write the word everywhere. I'm gonna make it a little bit fancy and math jargony. This is just basically saying everywhere. If we wanted to translate this like literally, this is saying for all x's that are real numbers. All real numbers. AKA everywhere. So that's what your answer would look like. Yeah. Yeah. If, say, like number 4 on the quiz tomorrow, I asked you to do something like this, you're going to give a very, very, very similar answer here, right? You have to, one, if I'm asking for everywhere, you need to make some kind of statement about having continuity at the non-interesting points, right? Oh, my function's continuous here. Direct substitution always works. Oh, my function's continuous here. Direct substitution doesn't always work, but it works for the x's that we're looking at, right? Direct substitution doesn't work at -1, but I don't care about what's going on at -1 when I'm using that function. Something like that. Yes, Harrison. Yeah, you would want to include. That's like the cherry on top. Make it super obvious for me. Like, one little line of, oh, this thing is equal to this is equal to this. Sure. So say again. You do need this. Yeah, you need to make some kind of say. If I'm asking you to show that it's true for all values of x, and you show me that it's true for -5/3, you've shown that it's true for a value of x, but that's not what I'm asking for, right? So this is the dealing with everything that isn't -5/3, and then this is the hard one, which is the dealing with like the actual interesting one, which is -5/3. It would be, let me say it this way, it would be very, very difficult for me to condense this more than I have. Like, this is a very thorough answer, but any less thorough would start to be wrong. So, yeah. Yeah. So you're saying, could I somehow like do this statement here when I'm down here? Um, I mean, we kind of have. If you're asking if you could like jargon it, yeah, you could. Like, you could take this statement that I have written in English, take this statement right here, and change it to the limit as x approaches a of of um of x squared plus 5x plus 6 over x plus 1 exists for all values of a that live between. Yeah, I would do the English personally. Values of a that live between negative infinity to negative 5/3, non-inclusive, because direct substitution works for all of these values. I don't know that that is a more condensed version. It would have to look something like that. Yeah. So what do you mean you did it all in the calculator? Right. Sure. So that is demonstrating step number 2. Yes. Yes. You have demonstrated step number 2. For step number 2, we're doing exactly what you said. Right. So you've demonstrated that the limit exists. When you show that the left-hand side and the right-hand side agree, you've demonstrated that the limit exists. But you would need some statement, and it wouldn't even need to necessarily be showing by plugging it in again. You could have this first statement be, or maybe you could include this as a second statement. This is what I was doing for one of my other periods, is if you do this step second instead of first, you could maybe say something along the lines of like f of negative 5/3 is equal to the limit as x approaches negative 5/3 on the left of f of x, which we know we already found to be negative 2/3, right? Like, that would be an okay thing to say. And you wouldn't have to recalculate it. I think you are creating more opportunity to mess it up by doing it, and I would not necessarily recommend it. So like, I am being very serious when I say that like it would be difficult to condense this more. And showing that the left-hand side and right-hand side agree is an important step, but it is one of 3 steps for continuity at one point, and the question is much broader than that. No bonus on the quiz. You mean on the test? I mean, I could write a bonus on the quiz if you wanted to. Most people don't. I'm not happy about the fact that most people haven't attempted the bonus. I would like to see an effort into it. And most of them are fairly approachable. I will say, I haven't looked at these tests yet. I am very hopeful on the bonus on this test because I did explicitly say it like 3 times in this class, and I didn't say it explicitly in any of my other classes. So, no, on the Unified. So, or no. Yeah. It was the Unified one. Yeah. It was, wasn't it like something about? Oh no, never mind. Those are right. On the Unit 6. I was expecting more on the Unit 6. Sorry. I was expecting more on the Unit 6. But it's fine. All right. No idea. It's a fair question. I have no idea. Let's take a look then at B. We're going to do something very, very, very similar for B. Again, the thing that I'm trying to emphasize here, precision is very important here. All right. I am asking you to demonstrate very, very like high, like things that have a very high amount of, I guess, like, what's even the word? I'm making big claims. I'm making very large claims. I'm asking you to make very large claims. That means that there's a lot of work that goes into showing that those large claims are correct, right? So this is f of x is equal to piecewise function, x squared plus 7x plus 6 over x plus 6 if x is not equal to 6, and it is c if x is equal to 6. Or sorry, negative 6, right? Okay. And again, I am asking for a demonstration of continuity everywhere, not just at negative 6. I'm looking for continuity everywhere. So certainly we are interested in demonstrating continuity at negative 6. That's probably going to be the interesting point here, right? Is looking at what's going on at negative 6. That's probably the one that will require some math. But for everywhere else, I still want to make some kind of statement that says, hey, just a heads up, I'm not checking these values because they're obviously continuous. It's like an obviously continuous kind of statement. So if negative 6 is the value of focus, the one I care about, we want to make some statement about what's going on if x, we could do something similar if x is greater than and if x is less than, but in this case, actually, we can just focus on what's going on if x is not equal to negative 6, because if x is not equal to negative 6, which of these two functions am I definitely going to be using? Yeah, we're only going to be using the top function. Okay, what is the only value for my top function where I would not be able to do direct substitution? Negative 6. So can I do direct substitution everywhere else? Yes, and since I'm talking about everywhere else, we are good to go to say that f of x is continuous because direct substitution is possible for x squared plus 7x plus 6 over x plus 6 if x is not negative 6. Maybe possible for all x's. The for all x's is actually probably worse. I like that better. Okay. That statement is necessary to demonstrate the thing that we are claiming is that we are demonstrating. All right. You need to have just some little blurb. We have easy give me continuity in most places. Now then we need to turn our focus to the point we actually care about, which is going to be at negative 6. Okay. What are the 3 things that we need to demonstrate for continuity? F of a has to exist for the starter. What is f of negative 6 equal to? What happens when I plug? What happens when I plug in negative 6? Do we know yet? It's c. It's whatever c is, right? All we're trying to do is show that it exists. Does c exist? Yes, we're good to go. That is all you need for step number 1. That'll be for step 3. So step 3 will be figuring out like what c actually needs to be. Here it's just whatever c is, we haven't found it yet. So you're always gonna just do like the number. Yeah, it's defined. Right, exactly. It's defined, right? And again, that would fail if like the inequality was exclusive on both, or if there wasn't like an or equal to statement, that would like cause step 1 to fail. There would just like not be a thing there. Okay. Generally speaking, step 1 is just like you look at it and you're like, yeah, it exists. Cool. Let's move on. Yeah. Okay. Step 2. What do we need to demonstrate for step 2? Left and right hand limit agree. So we need to look at the limit as x approaches negative 6 from the left. And we need to look at the limit as x approaches negative 6 from the right. For both of these, which function am I using? Left and right. We're using the, Harrison, sorry, you said it and I missed it. Top function, yeah. Notice not equal to -6 means that if I'm a little bit to the left of -6, I'm going to be using that function. If I'm a little bit to the right of -6, I'm going to be using that function. This is the limit as x approaches -6 from the left of x squared plus 7x plus 6 over x plus 6. This is the limit as x approaches -6 from the right of x squared plus 7x plus 6 over x plus 6. Can we, as things stand right now, do direct substitution? No. If we could, we wouldn't even be doing this. We would have just said we could do direct substitution everywhere. Let's move on with our lives. No, can't do direct substitution here. That's fine. What could then we do to try and get the x plus 6 in our denominator to cancel? Let's try factoring the numerator. What are two numbers that multiply to make 6 that add to make 7? 1 and 6. And what's going to happen with my x plus 6s? They are going to cancel. For both my equations here, this is the same as the limit as x approaches -6 from the left of x plus 1. This is the limit as x approaches -6 from the right of x plus 1. And do I have any more domain issues here? No, I do not. So what happens after direct substitution? -5 and -5. So does my limit exist? Yes, it does. We might say something along the lines of the limit as x approaches -6 of f of x is equal to -5. Okay. And then finally, our third thing, what do we need to be true in order for this to be continuous? Yeah, everything has to be the same value. So we need the limit. We kind of want to show, find the value of c such that. So we have that the limit as x approaches -6 of f of x is equal to -5. We have that f of -6 is equal to c. Therefore, what must be true? C must be equal to -5. Basically, yeah. That's often what the third one is. You do most of the work in step 2. You do a tiny little bit of work in step 1 sometimes. And then the third one is just like saying, hey, I found all the pieces. Here they all are. Look at how I did. Yeah. All right. How do we feel about B? How do we feel about this process? So like, again, mathematically, I think you guys are really solid on this. I think like limits mathematically are where it's that nice bridge of like conceptually you can get a lot of traction out of them. Mathematically, they're not like super crazy to figure out. The tricky bit then is how like verbally intensive all of this is. And I will admit, I'll be the first to admit that yes, that is true, that there is like a higher level of like just word stuff that we need to be able to do, which is kind of obnoxious. Just boxes to check, right? To like confirm that something is true, to show that something is true. So don't take shortcuts on this. It's one of those things that like you start taking shortcuts and your answer goes from like super, super solid to like complete nonsense very, very quickly. Even if you're correct, like for demonstrating it, don't like cut corners. So I will say today's lesson is quite short. It's kind of just a rehashing of things that we've already said. I'm also not super interested in it, so I'm going to go through it pretty quick. The main thing that I want us to be able to gain from this is the idea, one, of what these asymptotic limits look like, and then two, the idea of limits to infinity, because it's a very useful language to use for that. Before we do that, would it be helpful for the quiz tomorrow, which will not be on what we are covering today, but will be on continuity and things like that? Would it be helpful to look at another example like the bellwork? Should we do you want to do that first? Another bellwork example first, and then quick little lesson on asymptotes after? Cool. All right, let's try this one. First and foremost, what is the interesting value that we're gonna like focus on here? Well, just like the interesting X value. The 0, right? The X value that we're actually gonna like be placing a lot of focus on is just 0. That. But we would want some statement that just like regardless of what K and C are, our function is continuous. We could note that K times cosine of X and X squared plus 3 are both continuous for X is less than 0 and X is greater than 0 respectively, because direct substitution works for all those X's. Maybe that's the most condensed way we could say it. All right, some statement that like, hey, it works everywhere that isn't 0. We're just, good on that respect. Okay, what do we need to show in order to demonstrate continuity? First thing is that f of a exists. In this case, we're looking at x equals 0. So what is f of 0? It is c plus 3. Does that exist? Yes. Okay, that's like fine. What is the second thing that we have to demonstrate? Limits from the left and right match. So we need the limit as x approaches 0 from the left, which is going to be using which function? Top one. This is the limit as x approaches 0 from the left of x squared plus 3, which according to direct substitution is equal to 3. And then we have the limit as x approaches 0 from the right, which is going to be using which function? The very bottom one, right? So equals k times cosine of x, which direct substitution tells us is equal to just like k times 1. And since these must be equal, what do we know? K must be equal to 3. And importantly to note, k is 3 and the limit is 3 as well, right? The limit as x approaches 0 of f of x is also 3, which is good to note. We'll use it for step 3. What are we demonstrating in step 3? That they must equal. So the limit as x approaches 0 of f of x must be equal to f of 0, which means that c plus 3 should be equal to 3, which means that c is equal to 0. Did you get c equals 0? Then you're probably fine. The order of equality doesn't really matter. All right, questions with continuity. How's this feeling? All right. Relatively quick lesson. I am not super concerned about this stuff. Mostly just wanted you to be familiar with the idea that we can see infinities when we do this kind of limit stuff, which is something that we've seen before. It's just now we actually have the notation to be able to more accurately describe what is going on. So vertical asymptotes before in unit 2, I defined these as like what happens when the denominator gets really small and the numerator is staying the same, and we get this like explosive behavior around unregulated zeros and blah, blah, blah. None of which was particularly like mathy, none of which did a very good job. And that's because we didn't have this language. Now we do have this language. Now we can more accurately say what is happening. We describe a vertical asymptote as occurring when we have the limit as x approaches a from either the left or the right, it doesn't really agree, of a particular function, when this is equal to plus or minus infinity. And the thing to observe is this is normally going to happen when the denominator gets really small. Although not always. We'll see. Okay, so let's look at some examples here. Let's take a look at example 1b first. This is the limit as x is approaching 1 from the right of e to the 2 over x minus 1. 2 over x minus 1 all in that exponent there. So this is like e to the 2 over x minus 1 like this. If I'm looking at the limit from the right, what kinds of values am I going to be plugging in to this particular function? Give me an example. If we're doing this to the right, we don't have like a good way to do direct substitution. You have to do this on your calculator. What would be an example of something that you would pick that is to the right of 1? 2, but we want to get closer, so 1.1, 1.000000001, right? Values that are all close to 1, but a little bit above 1. What does that mean is going to be true about my quantity of x minus 1? If I'm only plugging in values that are slightly more than 1, it's going to be very small, and you're saying greater than what? Greater than 0. All the values are greater than 1. We're subtracting 1 away, therefore all the values will be slightly positive, right? Very small, very slightly positive. And so the limit as we are approaching 1 from the right is going to be e to 2 divided by a positive small number. Which, what happens when I make my denominator really small? My number gets really big. This is the same as, we could think of this almost as like e to the power of infinity. And what's going to happen when I take e, which is a number greater than 1, and raise it to a stupidly large power? It's going to get stupidly large. So 2 divided by, so try it on your calculator. Try doing 2 divided by a number that's really small. Yeah. Yeah, some stupidly large. I mean, you would imagine that the smaller you get, the bigger that number is going to get. So you just make that number infinitesimally small and you get a number that's infinitesimally large, or infinitesimal is small. So infinitely large, I should say. Okay, I will admit I have done something horrible, math crime related here. Technically speaking, am I allowed to plug infinity into something? No. Infinity is not a number. There's not like a value of infinity that I can plug in. All we can do is plug in numbers that get us closer and closer and closer and closer to infinity. I wish I had some kind of notation that allowed me to describe what was happening as I got closer and closer and closer and closer to a desired value, rather than what's actually happening at that value, except that's exactly what we've been building over the past week. Another better way to communicate this idea of quote unquote plugging into infinity would be to say that this is the limit as we'll maybe say like A approaches infinity of E to the power of A. So like you don't actually ever plug infinity in, but you're basically plugging infinity in. So like it's kind of good enough. And I'll be 100% honest, while this is what you should write, this is what I do in my head. So, just a quick thing to note that this is gibberish nonsense. This is taking that idea and making it not gibberish nonsense. All right, let's try the same thing, but with B here, or sorry, with A here. Instead of approaching from the right now, we are approaching from the left. What is that going to change about this expression? It's going to be E to the 2 over something still very, very small, but now negative. What does taking my exponent and turning it negative, what does that do to my expression overall? What does a negative exponent do? Does it turn the overall negative? It takes the reciprocal. So this is the same as 1 over E to the 2 over really, really, really small. Which we said was basically the same as 1 over E. Okay, I'm going to be bad again. E to the infinity. Yeah, Harrison. Well, I dealt with the negative by taking the reciprocal. You're right that if I hadn't done that, it would be negative infinity. 100% right. Good call. And what's going to be happening as my denominator gets stupidly large? It's going to get very, very small, and it's going to approach 0. 1 divided by a billion is very close to 0. 1 divided by Google is very, 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 very close to 0. And again, this is poor form. You would maybe say something like the limit as A approaches infinity of 1 over E to the A, which is equal to 0. What's the question, Hans? No, not always. It'll depend. Yeah, it doesn't necessarily, there's not like a pattern here that I can say. And I could give you functions that converge to various things at different points. But I will say for these vertical asymptotes, like generally, yeah, you're going to have some kind of convergence towards. That's what I'm trying to demonstrate is the convergence towards positive. Well, convergence is a bad term here, but moving towards infinity. Let's look at another example. So this is the limit as x approaches 0 of 1 over x squared. In order to look at the overall limit, what am I actually asking us to do? It's 2 parts. How do I find the overall limit? Left and right, see if they agree. So this is the limit as x approaches 0 from the left of 1 over x squared, and then the limit as x approaches 0 from the right of 1 over x squared. What happens when I plug in the number that's slightly less than 0 and then square it? What's going to happen to it? Turn positive. So 1 divided by a very, very, very small positive number is going to do what? Go to infinity. And then what happens when I take a very, very small positive number and square it? It's going to be probably smaller. Small, the times small gives you even smaller, but same idea, right? It's going to be a very small positive number, and 1 divided by a very, very, very small positive number is going to be very, very, very large. So in this case, do our ends match? Yes, they do. And so we can maybe say here that the overall limit is infinity. Now, I will say that is another way of saying that the limit does not exist, but it's a different way of saying that the limit does not exist than saying that the ends don't agree, right? Here, the limit does not exist because the left and right-hand side disagree. Here, the limit does not exist because we don't have a limit, we have explosive growth. But we can be more descriptive than just saying DNE. We say infinity as that specific DNE. Because, like, is it actually equaling infinity? No, we're just saying it's growing without limit. Sure. Okay, questions with our kind of potential for vertical asymptotes? No, this is not on the quiz. Fair game on the test, but again, I'm not super interested in it. The main thing that I want us to actually take away, though, is the idea that we can take the horizontal asymptote language and also convert it into talking about limits. Horizontal asymptotes, if you would recall, are end behavior descriptions. So what happens as x gets really, really big. These are ultimately limits as x is approaching plus or minus infinity, which, if the horizontal asymptote exists, are going to converge to some value of L. So let's take a look at some examples. For instance, I'll leave A as an exercise to the reader. Let's look at B and C here. Limit as x approaches infinity of 4x squared over 2x squared plus 1. As x gets really, 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 really big, what part of this equation really just does not matter anymore? There's like one thing here that's just not going to be able to contend with the fact that we're looking at, like, the plus 1 is just too small for us to care about. And in fact, anything other than the leading term is too small for me to actually care about. This is going to be 4x squared. Say again. Yeah, you're just going to ignore the plus 1. You're just going to basically pretend it's not there. And then the question is, does this expression simplify? What is this going to be equal to? 2. So the limit is 2. Horizontal asymptote, exact same thing, right? We did the exact same process. You ignore everything other than the leading 2 terms, take that quotient, and then there you go. Well, let's take a look at C. So as x is getting really, really big, what stops mattering? The plus 1 again. So this is, from the numerator, the 4x is going to determine what's going on. From the denominator, the 2x squared is going to determine what's going on. How does this one simplify? As x approaches infinity, 4 divided by 2 is a 2, and x divided by x squared is an x. But we're taking the limit as x is going to infinity. And so what happens when I do 2 divided by a very, 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 very large number? 2 divided by when the denominator gets big? 0. So we can't, like, literally plug infinity in, but this is like as close as we're going to do to saying plug infinity in and see what's going on. All right, questions on section 4? All right, we've got about 10 minutes left. If you guys have not yet finished your classwork, you have the rest of this time in order to do so. All right.
Yeah, take a road. Especially if you got Monday. They always add the Germantown Thomas.